Thank you, Patrick. Hi, everyone. It's really great to be here this morning. It's a real pleasure. I'll share with you all how we at Google DeepMind are accelerating scientific discovery with AI. I'm Joëlle Barral. I've spent a bit over a decade at Google, including at Google X, our moonshot factory, and at Verily, our sister company dedicated to the life sciences. I'm now with Google DeepMind, our world-leading in-house AI research lab. And if there is just one thing I'd like you all to remember from this talk this morning, it is that we have entered a new golden era of discovery that leverages AI as a general-purpose tool. At Google DeepMind, our mission is to build AI responsibly to benefit humanity. If we want to frame the moment we're in, and I think this place is a fantastic reminder of that, it's helpful to reflect on history. The Industrial Revolution captured physical power, moving us from farming to manufacturing. It was about building. The Information Revolution changed how we live, work, connect with each other. It was about sharing. And now, with artificial intelligence, it is about understanding. We believe that AI will power a fundamental social and economic transformation in the world, and it will do so through the sciences. So what does a scientific revolution from AI look like? I'd like to start with a very concrete example from molecular biology, AlphaFold. Proteins are frequently called the building blocks of life because almost all biological processes in every living thing depend on proteins, from the twitching of your muscle fibers to the firing of your neurons. And in 1949, Frederick Sanger correctly determined the amino acid sequence of insulin, one particular protein. Think of that amino acid sequence as a string of beads, where each bead is one among 20 letters. He got the Nobel Prize in 1958 for that discovery, and that started molecular biology as a field. Scientists in molecular biology were then very keen to determine the shape of a protein, its 3D structure. And it took us 70 years to go from understanding the amino acid sequence of insulin to understanding the 3D structure of 200 million proteins, nearly all proteins known to humanity, thanks to AlphaFold. Knowing that 3D structure matters if you want to understand control or modify a protein's function. And finding a computational solution to this grand challenge is far from trivial. It's known as Leventhal's paradox. There are about 10 to the power 300 conformations that a typical protein can take. Enumerating all of those possibilities would take longer than the age of the universe, and yet, in nature, proteins fold within milliseconds. Demis Hassabis, DeepMind's co-founder, John Jumper, one of my scientific colleagues, were awarded the Nobel Prize in Chemistry in 2024 for AlphaFold. But importantly, that work was only possible after decades of experimental work, and we had in the protein data bank 170,000 structures that had been determined experimentally and collated, and that allowed us to then leverage, compute, and figure out how to crack that challenge. We open-sourced the AlphaFold code and created a freely available database of protein structure predictions, enabling researchers worldwide to use it and build upon the technology. It's now been used by more than 3 million scientists worldwide, and it's become a standard tool in the biology toolkit. It's answering some of the most pressing questions in biology, from breaking down plastic pollution, racing against drug-resistant bacteria, or finding cures for neglected diseases. Now that we've explored one particular example in molecular biology, let's take a step back. Why would a company like Google DeepMind be interested in protein folding in the first place? And what does that tell us about AI-assisted scientific discovery more broadly? You might remember that Google DeepMind started by solving games. We started with Atari, training AI only on the raw pixel input, with the goal of maximizing the score. And it learned how to win on its own. It wasn't just Atari, it was every game. Our most notable games breakthrough was mastering the ancient and complex game of Go, arguably the pinnacle of games. Go is incredibly difficult for a computer to solve because it's so complex. AlphaGo learned to play Go by playing against itself millions of times. To test its skills, we played against the 18-time world champion Go player Lizzie Doll, and more than 200 million people watched the game. AlphaGo won 4-1. It didn't just win, but it also came up with creative strategies never seen before. For example, the famous move 37. Many people thought it was a mistake. It wasn't. It was a new strategy. AlphaGo clearly demonstrated that these learning systems were able to learn something useful. AlphaGo and AlphaFold have 3 ingredients in common. That's an important slide that I would also encourage you to remember. The key ingredients we like to see before we tackle a challenge with AI: a massive combinatorial search space where neural networks can effectively guide search, a clear objective function or a metric that we can optimize our hill climb against, and either lots and lots of data or an efficient simulator, a way to produce lots of data. AlphaGo and AlphaFold weren't the only breakthroughs that happened in AI over the years. In parallel, we were also building the foundations of the generative AI revolution, starting with the Transformer paper in 2017. We have now entered what we call the Gemini era. Gemini 2.5 is our largest, most powerful model. It's powering the rest of our AI innovation, including in the sciences. We've also created the Gemma family of models, which offers different models optimized for specific use cases tailored to specific needs. And Gemma is an open family of lightweight, state-of-the-art models built from the same research and technology used to create the Gemini models. I'll pause here just to quickly introduce 3 concepts because I'll be using those acronyms. You might have seen embeddings. Embeddings map semantically similar tokens or words into mathematical vectors. It captures how close in meaning words are. What London is to England is the same as what Rome is to Italy. I'll get back to that towards the end. You've all experienced large language models, or LLM, through chatbots. They are largely based on next vector prediction. Could you please open the window is a lot more likely than could you please open the barks. I actually don't even know why we would have a bark right there. And Gemini and Gemma are examples of large language models. And then reinforcement learning, or RL, describes a set of algorithms that learn to adapt behavior to achieve preferred outcomes, maximizing a reward. AlphaGo training, the AlphaGo training process, for example, included RL. By the way, I generated this image of a horse eating its sugar reward with Nano Banana. And if you haven't tried it, you should stop listening to me and just start playing with Gemini. So how many of you here had already heard of either AlphaGo or AlphaFold? Yeah, most of you. But I would like to now share with you more recent examples across different domains that will really help you appreciate the acceleration we're seeing. I'll not be able to cover everything in the sciences. I won't talk about math. I won't talk about quantum. I just heard that you'll have some of that later this week. But I'll start with healthcare and robotics to show you the power of large language models like Gemini and Gemma for the sciences. I'll then briefly wander into physics, where you'll appreciate that breakthroughs in reinforcement learning and control can go beyond robotics. And they're very strong illustrations of the clear objective function I was just telling you about for AlphaGo and AlphaFold. And then I'll share a few examples in sustainability where foundational models can go beyond large language models. Web data gave us large language models for the most part. If we can now leverage Earth data more broadly, what can that help us understand about our planet? So that will be the last part of this talk. Let's start with healthcare. Our researchers have been pioneering understanding what the advent of large language models means for healthcare. Medicine is very often mediated by language, but it also presents a unique variety of data, text, images, videos, ECGs, et cetera. When we're probing the human body in clinical exams, but also when we are going deeper into the biology, for example, with pathology slides. And this slide here reflects this variety. We started with MedPalm, Flamingo CXR, Amy, MedGemini, MedGemma. They were all about understanding lab results, understanding medical images. And then the personalized health assistant was about understanding wearable data. We actually announced a public preview with Fitbit earlier this week. TX LLM, TX Gemma, cell-to-sentence are about probing the biology. Let me tell you a little bit more about MedGemma, which is our most capable open model for multimodal medical text and image comprehension. It's based on Gemma 3. It's a good starting point. It's not meant to be an end solution. It's a starting point for developers and researchers to then further fine-tune and build their own healthcare-based AI application. It's small in size, which means it can also run efficiently on many different surfaces. The reason why I like this example is that a couple of years ago, when one of my researchers came to me with something that was looking like this here, a chest X-ray and the embryo of a report, I really thought that was going to be impossible. It would do some useful things, once in a while, but that really sounded like magic at the time. And here we are. We now have examples in which MedGemma can make reporting for radiology scans a lot easier. Here it's a patient who had a chest X-ray. MedGemma is reviewing the scan, explaining what the findings mean. It has found a mass in the right lung that is suspicious for cancer. It's looking through the key review areas that no other abnormalities has been reported. And then it can summarize the findings and recommends a CT scan. And then we can look at that CT scan. And again, MedGemma can provide a comprehensive review of the scan, clearly describing cancer and recommending a referral. This is one of the many things that MedGemma can help do. Again, it's not approved as a med device on its own. From Gemma, we've also derived TX Gemma. You can think of TX Gemma as a family of open models that can help with drug discovery. So it's able to understand regular text, but it's also able to understand the structures of different therapeutic entities like small molecules, chemicals, proteins. I'm putting a lot of QR codes because I won't have time to go into details, and I really encourage you to go and read the corresponding published paper underneath if you're interested. Last week, as part of our research collaboration with Yale, we released cell-to-sentence scale 27B, so a new 27 billion parameter foundational model designed to understand the language of individual cells. It's also built on the Gemma family of open models, and it's a new frontier in single-cell analysis. What's important here, and that was the publication last week, is that this model was able to generate a novel hypothesis about cancer cellular behavior, and we have since confirmed its prediction with experimental validation in living cells. And that's really where we are with a lot of those large language models that are helping scientists, making sure that the suggestions they're making can then be independently validated experimentally. And then that's really how we know that they are helping us find useful pathways. Here, this discovery revealed a promising new pathway for developing therapies to fight cancer. So without any good transition, I'm now going to tell you a little bit about robotics, because it's another field where the advent of large language models has completely changed the game. It's changed the game in healthcare because language is really the mediator in medicine. But it's also changing the game in robotics because for many years, if you've ever programmed a robot, you had to go to a very, very low level and teach the robot to go from point A to point B in a very manual and kind of low-level way. Now, large language models have made interacting with robots a lot easier. Of course, robotics is both a scientific and an engineering discipline, and this keynote is supposed to be about scientific discovery, not really robotics, but I couldn't resist to show you some of the recent progress. It's relevant in the context of this week, I believe, because of how virtual worlds and simulations have always been so important for robotics. So in robotics, we're closing the gap between what we call the seem-to-real gap, the gap between simulations and reality, and the acceleration is palatable. So I'll let you extrapolate that to your favorite field that also requires lots of simulations. Through what we call vision language action models, robots are able to figure out how to do things that they were never explicitly programmed to do. So you no longer have to tell them to go from point A to point B. And that was impossible just a few years ago. What we call Gemini Robotics 1.5 enables a robot to perceive, think, use digital tools, take action to solve more complex multi-step tasks. What I'm personally really excited about with this Gemini Robotics 1.5 launch just a few weeks ago is the fact that for the first time, we've also demonstrated the ability to transfer new skills from one robot to another, so from one hardware to a different hardware. And I'll play a very quick video here, trusting that everything will work.
This is a good way to understand the learning across embodiments. Aloha has actually played quite a bit with the wardrobe scene. Apollo here has never seen this scene, and we're going to ask it to do something completely new, which is to open this door right here, which is something it's never done before. A little bit more. Can you ask it to pick up the clothes in it? So this is a great example of a completely new motion that is able to learn with the Aloha robots and not just transfer here.
Wait, that's just one example. And again, I encourage you to look at this code and explore more videos. What's happening in robotics now, and I know, robotics is like AI. It has had a few winters. It has had a few, very exciting eras. What's happening in robotics now is unprecedented. And I think AI and generative AI in particular, this ability to really teach robots tasks in a very general way is quite remarkable. So I've shown you the power of language in fields like healthcare and robotics. LLMs have enabled breakthroughs that were just unimaginable a few years ago. Let me now go back to scientific problems that have a clear objective function, like AlphaFold. AI is, for example, allowing us to push the frontier in physics. It's not just abstracting things out and solving the theory. It's doing that and then ensuring that the insights translate experimentally. And just like with cell-to-sentence, we do that through collaborations. So a first example here is deep loop shaping, which we announced last month. The LIGO detector in the world is the world's most sensitive instrument. It's meant to detect ripples in space-time, also known as gravitational waves, which are generated by massive cosmic events, like when two black holes are merging. To be able to detect these events, these ripples, the LIGO detector has to measure length changes with subatomic precision, 10 to the power minus 20 meters, equivalent to measuring the distance to the nearest star, roughly 4 light years away, to an accuracy smaller than the width of a human hair. So if you've ever aligned mirrors on a tabletop when you were in undergrad, you know that it's not trivial. LIGO stands for Laser Interferometer Gravitational Wave Observatory. It's somewhat akin to those Michelson interferometers you might have played with in earlier years. They use a control system to counteract seismic noise. However, traditional controllers often introduce their own disturbances, some of a high-frequency hiss that will limit sensitivity. Our collaboration with Caltech and the Grand Cecil Science Institute introduced an AI technique that we've called deep loop shaping, which uses reinforcement learning, which uses RL, to dynamically optimize the control system. This graph summarizes the results. I won't go into too many details, but what you're seeing here is the LIGO's noise budget and controller performance. In purple is what we've measured, the strain noise. In red is the currently operational linear controller. In blue is the noise contribution from our RL policy as run on that LIGO Livingston Observatory about a year ago, December 5th, 2024. And dashed green is the control design goal derived from the quantum limit by applying a design margin of 10x. So we want the control noise to be below that curve. And what you're seeing here is that deep loop shaping algorithm was able to build a model from a lot of the interferometer measurements. Then it used it as a learning environment and leveraged frequency domain rewards as the compute rewards. And then that optimized control policy was deployed for real on that interferometer. And so it's boosting the sensitivity, especially at lower frequency. That's the shaded blue here. And it's allowing us to detect potentially hundreds of more gravitational wave events per year. Without any good transition either, a different physics domain in nuclear fusion, where we all know that power is the holy grail of energy, clean, essentially unlimited energy. One of the many enormous technical challenges in making fusion a reality is how to control plasma inside the reactors. It's hotter than the sun, and we have to avoid the plasma touching the walls of the reactors. We've partnered with the Swiss Plasma Center, which has an experimental reactor in Lausanne, to successfully develop and use reinforcement learning to control the plasma inside the reactor. And it has to adjust the voltage in the magnetic coils of the reactor 10,000 times per second. So as we've been able to use that system to reshape the plasma into different shapes and see how that optimizes the fusion process. It also came up with different shapes that hadn't been seen before and were then, again, validated experimentally. This brings me to the last part of my talk. Foundation models have changed how we think about healthcare and robotics. AI has brought new solutions to physics problems. And we all thrive to better understand our planet. So what if we trained some of those foundational models with Earth-specific data? Historically, weather forecasting is done through numerical weather prediction, leveraging physics to simulate atmospheric behavior. We use observational data from weather stations and satellites, for example, the temperature, wind speed, et cetera. And these models then process the data with complex and time-consuming calculations performed by supercomputers. We trained a few different models to improve weather predictions. And for example, GraphCast is trained on historical data from the European Center for Medium-Range Weather Forecasts, and it delivers a 10-day weather forecast at unprecedented accuracy and under 1 minute. And that inference time under 1 minute is also a very strong differentiation from the more traditional techniques, ours when using a conventional approach. And then beyond weather, we've introduced the Alpha Earth foundations. If you look at this visual, you see a montage of a lot of different satellite imagery, tiny snapshot of the diversity of the planet. You see agricultural fields, mountains, complex forest canopies, et cetera. The challenge with Earth data is immense because it's a lot of data, petabytes in scale. It's very diverse and noisy data. It's captured by many, many different sensors. It's suffering from clouds and shadows, seasonal changes, et cetera. So to truly understand and map our planet, we needed a foundational AI model capable of abstracting all of that. You can think of Alpha Earth as a language model, but instead of learning the relationships between words, it's learning the relationships between every point on Earth. And so it's trained to fuse all of those satellite modalities. And it's creating a holistic, continuous understanding of the land, of the weather, of the ecology, regardless of the quality of the input data. It's a new foundation for unprecedented global mapping. And so how do we achieve that level of detail? I told you embeddings were important. This is a concept here called satellite embeddings. So this illustrates the process. We start with multi-source Earth observations on the left, everything from raw satellite images, weather data, LiDAR measurements, et cetera. And then the foundation model takes all of this complex high-dimensional data and compresses it into an annual embedding, which is simply a dense numerical vector. That vector is the fingerprint for that specific location at that specific time over the course of a year. And it abstracts away all the noise, captures the meaningful environmental information. For example, where crops were grown, what type of soil do we have, what's the carbon content, et cetera. And the result is a global embedding field, which we can think of as a common language for the planet. It's a data set that is already helping countries map with new levels of details uncharted ecosystems that were previously too difficult or too remote to understand. It drastically lowers the barrier to entry for using powerful AI for global challenges, like tracking deforestation or helping with sustainable development. So in the same way that AlphaFold has revolutionized biology, we believe that we're entering a new golden era of discovery, where many scientific fields will be revolutionized by AI. This is what we call science at digital speed. It's therefore critical that we train the next generation of scientists accordingly, and that we bring diverse perspectives from many fields to ensure that AI benefits everyone. And with that, I thank you for your attention. I believe we have time for a couple of questions.
Thank you so much. Thank you so much, Joëlle. A couple of comments and then questions. First, I think we are all amazed by the depth and breadth of what you have been presented. I think it's almost a table of content for this week. There are so many connections with all the sessions you are going to see in energy, in healthcare, so thank you so much for that. Needless to say, I don't know if you guys coined the term transformer because you knew how transformative it would be for the whole society, but I think it was pun intended, I think. And so I have one question to start with, and after that we'll open to the room. Demis Hassabis, CEO of DeepMind, always comes back when he talks to the fundamental questions, like nature of reality, how do we fundamentally learn? So in that regard, what are the next milestones for DeepMind?
This is such a big question. I mean, as I hope you got a little bit of a glimpse, we've been shipping a lot and fast, and so I don't think it's one milestone. I think there are lots and lots of things that are brewing. If some of the things that we are really thinking about from a research perspective is assuming AGI, that is AI as we know it today, but really capable in many fields.
When is it the usual question?
That's the usual question.
When?
But without answering that question, assuming it comes, what will happen next? And that gives us the right framework to anticipate, especially how we want that technology to benefit humanity. So if you think about the ways we currently interface with our digital world, is that the ultimate embodiment? Is that really what, as a society, we want to see? Or are there other ways that we could really make that technology be beneficial to us personally in our personal and professional lives? And what does that look like? So we spend quite a bit of time now really thinking about the AI agents, all of us, and society more broadly, and what those interactions might look like.
The new kinds of relationship between the real people and the virtual agents. Any questions from the room? Over here.
Hi. Amazing talk, first of all. Thank you. Do you think that LLM and token-wise architecture will be the core foundation of generative AI, or do we need something else? And as we progress, we create more and more virtual AI content in the internet, and our models are trained on that. How do we not echo chamber ourselves with the models?
Yeah, those are two good questions. So the first question is, is transformer all you need? I think many of us are wondering, is this the last breakthrough? I think if anything, we always know that the answer to that question is always no, right? So there will be, I think, more architectural changes. Will that have the impact of that particular paper? And what is that a prerequisite to some of the future breakthroughs? I don't think there is a simple answer to that, but we're definitely continuing to do a lot of research in various architectures and trying especially to make things more efficient, both at training and at inference time. And then to the question of data, and I think that's also a very acute question this week, given all of the twins and virtual worlds that allow us to actually generate data when we don't have enough data for rare diseases or other things. We have ways to label data when it's AI generated, and so we're also, with things like SynthID, taking lots of care into making sure that we don't fall into the trap you're mentioning.
Yeah, in fact, if I may just add, we are going to issue a paper called Representation is Maybe What You Need, because of course with modeling and simulation you can do what if and extend on the training set with learning experiences. Any other questions? here. With the mic here.
Thank you very, very much. This was like an unbelievable review, so thank you so much. I come from the healthcare sector, and I'm particularly interested in the applications of AI to the interface between, say, medicine or healthcare and the patients. And so this is maybe more of a philosophical question for you, but I'd like to know your thoughts about in the efforts that we make to democratize access to healthcare. It's clear that we're leaning towards AI solutions to optimize the content of the healthcare product, but how do we facilitate the transition going from machine-based healthcare delivery to the human interaction that has traditionally existed between patients and physicians, for example? How do we smooth that out, that transition from AI, say, to a human interaction?
Yeah, thank you for the question. I think that also echoes your question about, what are we thinking if we assume AGI. The one way I like to answer that question is, how many of you have actually leveraged a conversational agent, an LLM, Gemini, or some other one, to understand your health, either to better understand a lab report or some symptoms you are having, or have you ever asked any health-related question to those things? Okay, half of the room, roughly speaking. How many of you have done that in a doctor's office? There's some brave people here. Many people don't dare, right? Like pulling up their favorite chatbot and then interrogating that, at the same time interrogating their physician to understand which symptoms they're having. And we haven't yet figured out what is the best embodiment between the AI, the models that are incredibly capable, right? Like with MedGemini and other papers, we've shown that actually those models are better than students are at answering a lot of clinical scenarios, and even panels of experts now, not just students. So, the models that are incredibly capable, the physicians that, of course, know you personally, but also have a lot more context about you and the surroundings, and et cetera. And you as a patient that also, you have a lot to say, and you know yourself, and you know which things might work or might not work. So this triad of patient, physician or physicians, and AI and or agents, that has not been properly figured out yet. So there's also a lot of work to really, again, envision how we can best leverage this incredible technology that we now have at our disposal. And maybe the other thing that's important is, and I think that's also what you're alluding to, intelligence is not all you need, right? Today, the healthcare system is challenged in many different ways, and access to knowledge is only one of the things that we need to figure out to really make people healthier globally. So it's not the only ingredient here.
I think we can thank again Joëlle for this amazing talk. Thank you so much. Thank you so much. Very, very proud to have had Joëlle with us.